When we look at an algorithm, we want to try to optimize our time and space complexity. Time is how long it takes the algorithm to run, and space refers to how much memory it takes to run. Big O notation is a standard mathematical notation that shows how efficient an algorithm is in the worst case scenario relative to its input size. And there are two ways that we can evaluate the big O of an algorithm. The first one, which is what we're going to talk about in this lecture, is experimental. The second one that we can talk about is going to be theoretical. So experimental is honestly kind of what it sounds like, right? So as we add more elements, you can envision a graph, and we'll say this is 0, and we'll say 1, 10, 100, 1,000, and then, so on and so forth. And this would be n for our input size. And then on this axis, we would have time. And you can imagine as the input size goes up, we see that we have a linear line. So with it being linear, we can represent this as t of the input size is equal to an plus b. So as our input size goes up, the time is linear according to the input size. So now when we evaluate this, right, so when we're evaluating our algorithm, there's two things, that we want. We want less time and less memory. These are ideal for an algorithm, and more time and more memory are not ideal. So again, we can look at another graph here where we have our time and our input size, and we can also have a graph that looks something like this, and this would be quadratic. And so we can say for this, to represent it, t of n is equal to an squared plus bn plus c. So we see we have 2 here, but then up here this is 1. So our big O notation for this would be O of n, and then our big O notation for this would be O of n squared. So we don't care about coefficients, so technically, we can get rid of these because, as I said, we don't care about them. We care about the highest power, which in this case is 2, and then in this case it's 1. And that is how we're able to represent our big O notation. And so if you wanted to do experimental evaluation, then you would create a benchmark for your program, and you would run it, and you would have input sizes of 1, 10,000, 1,000, 10,000, and maybe even 100,000. But in reality, sometimes, like if you ran 100,000 as your input size, depending on what your algorithm is doing, that could take a substantial amount of time, and you might not have that time to waste. And that is where theoretical evaluation comes in, and we will talk about theoretical big O notation in the next lecture. So now we're going to talk about theoretical evaluation. So remember, big O, there's 2 things that we need to keep in mind. The first being, we do not care about coefficients. And we will abbreviate that as coef. And the second thing is we only care about the highest power. Right? So now let's look at some examples of this and how we might be able to evaluate this. So let's say we have a vector, and let's put some values in here. We'll go 5, 3, 6, 1, and 8. And for our first algorithm, we want to find the largest number. The largest number, right? So you look at this and you say, okay, well that's pretty easy to do. All we need is a simple for loop, for x in the vector. Find the highest, and that we can do that using a simple if statement, right? So for this iteration right here, this is going to be an iteration. We know that x is going to be the value in here, right? So that's how many times we're going to go through. And for x in vector, well, this is going to be the length of our vector. So this correlates to n for how many items we have, right? And so by doing this find the highest logic down here inside of this iteration, we can logically conclude, since we're only having to iterate through the vector one time, that our big O notation is going to be O of n. And why is it O of n? Because we're only going through the vector one time, right? So now let's look at a slightly different example. Let's say we want to sort the vector, right? So for this, we'll do another for loop, and we'll say for I equals 0, I is less than or equal to n plus 1, I plus plus, right? So that right here alone, again, is the same as above, and that is O of n. Well, for us to sort it, we need to be able to compare and swap values in here. So we need to have our index here for I, and then we're also going to need another for loop, and we'll say it is j, and we'll start j at 1, right? Because we want to be able to compare I and j. So then we'll say j is less than or equal to n, j plus plus, and we'll say our big O notation here, let me clean that up, is O of n as well. And these are nested, right? Because we have O of n here, and then we have another for loop below it, which is also being executed every time that this for loop gets ran right here. So we have our nested for loops. We do our compare and swaps to sort the vector out. And with this being a for loop, and then we have our open bracket, and then we have our other for loop right here, and let's label these, bracket A, bracket B. Well, we close bracket B here, and then we close bracket A there. And what happens with this is that for every iteration in this A for loop, we're going to iterate through this loop as well, right? So I just want to make that really clear. And with that, we're going to iterate in twice, right? And with that means that we're going to have an exponent of 2. Or our highest power, yes, is 2. So our big O notation for this would be quadratic, as we showed in the experimental. And then our one up here, this is linear. So obviously O of n is more performant than O of n squared. And then if for some reason we had another for loop, so if we added another nested loop, for loop, well, now our big O notation would be O of n cubed, right? So hopefully that makes sense, because theoretical is a lot more time considerate when you're trying to evaluate your algorithm. And I wanted to talk about big O notation early on in this course as the first thing, because as we go through and look at all these different algorithms and data structures, I want you to be familiar with what the big O notation of that algorithm or data structure could be. And I want you to try and compute the big O notations for some of these algorithms and data structures as we go through this course, so that you're able to evaluate their performance, and maybe you can even enhance them to improve their space and time complexity. So it's really important that we really understand what big O notation is. So if you have any questions about it, please ask them in the Q&A section before continuing on in this course, because I really want it to be clear as to how you can compute the big O notation of an algorithm.